All right, we need to talk about collision theory, which is our theory behind what is going on with kinetics. So no, kinetics is still going to be empirical. We're still going to have to go to the lab and get rates, but on a microscopic level, we do have a theory, and that is collision theory. All right, collision theory. So let's imagine that we have two HI molecules and we're trying to make iodide and hydrogen. So let's take and imagine that we have hydrogen iodide coming in and reacting with an iodine and a hydrogen. And they're going to come in and they're going to react like this. Well, if this happens, the hydrogen is going to stick to the iodine, and that's not going to help because we don't want hydrogen iodide. We want to make iodine and hydrogen. So the first thing we have to do is we have to say these have to come in and collide in the correct direction, the correct orientation. The other thing they have to do is they have to hit hard enough, put in enough energy to break some bonds. Now that is the basis and the start of our collision theory. So again, if we have CO reacting with O2 and we want some carbon dioxide, we have to have the carbon hit the oxygen, because if the three oxygens hit, that's just going to give us ozone, which is not what we want. So the orientation of the colliding molecules partially determines whether the reaction will occur. We draw this out on a potential or energy diagram. So extent of reaction, that means that we have reactants going into products. Up here on the y-axis, we have energy. And as our reactants come together, they are going to have enough energy to break some bonds and for things to happen. Now, we've seen delta H. Delta H is the enthalpy, the change in the overall energy between the bonds. This in this case would be exothermic, but here what's not what we're looking at. We're looking at the energy required to start the bonds breaking, and that is activation energy. Activation energy is shorthanded as an E sub A. Figure out the activation energy, you're going to have to go to the lab and figure out how fast this is going to occur. This top right here of this hill is called the transition state. This is the space, or what it looks like to go between reactants and products. So if we had a carbon monoxide reacting with the oxygen, our transition state would look like our C, O, and we know it won't be in this direction. We know we have to have the O here, and we'd have the other O coming from the oxygen, and the transition state would be this interaction between the carbon monoxide interacting with this oxygen. And this right here would be our transition state. It would then break this bond and go down into products. So, activation energy. Okay, so looking back at E sub A, and we're going to consider the rate of the reaction, which is what we're interested in looking at, versus temperature. Now, the E sub A is what it is. You're going to go to the lab, you're going to measure it. But we can increase the rate by increasing the temperature. We know that as the temperature goes up, this rate here is going to go up. So if we start out at an original temperature, some sort of T1, and we go up to some temperature T2, we're going to find that the number of molecules that have enough energy to go over this barrier is going to increase. Therefore, the rate is also going to increase. So here, as the temperature goes up, the rate is also going to go up. Now, we got an equation that predicts this for us. So we have an equation for this. This is our Arrhenius equation. Note this is a nice exponential, which we're used to at this point. If we plot the rate constant here versus the temperature, we note that the rate constant goes up exponentially as a function of the temperature. And with this, we can get our equation. Now, we don't tend to like exponential forms, so we're going to take the natural log of both sides of this and see if we can get a linear form of this. The linear form of the Arrhenius equation is this. If we plot the natural log of the rate constant versus 1 over the temperature, in kelvins, we're going to get our graphing form of this, such that our slope here, m, is going to equal minus E sub A over r. So if we go to the lab and we see how the rate constant changes as we change the temperature, we can get the activation energy for this reaction from the lab data. Now, like the Clausius-Clapeyron, and by the way, this is just the same equation, we're just changing our delta H for an E sub A, we can have a two-point form. So note the previous was for the lab, and when you graph, this is for a nice homework question. And to do this, we're just going to plug in just like we did the Clausius-Clapeyron. So we're given the activation energy. We're given that the rate constant that we're starting with is 2.5 times 10 to the minus 2 units per second at a temperature of 15 degrees Celsius. Well, we know that our temperature has to be in Kelvin, so that's 288 kelvins. We know that we're looking for our rate constant at a temperature here of 37 degrees Celsius, which is 310 Kelvin. Our E sub A, it's 48 kilojoules per mole. And we can look up our R value of 8.314 joules per mole Kelvin. Now we know we're going to have to put our activation energy in joules so that our units work out, and we're just going to plug it in. So the natural log of K2, which is what we're solving for, over 2.5 times 10 minus 2 per second. Doesn't matter what these units are. Whatever the units are of K1, K2 will have the same units. It's going to equal minus 48 kilojoules per mole. Put it in joules, 1,000 joules per kilojoule, divided by 8.314 joules per mole Kelvin, multiplied by 1 over, we need T2. T2 is going to be 310 Kelvin, minus 1 over T1, which is 288 Kelvin. Everything on this side right here is just a number, and that works out to be 1.42. So the natural log of K2 over 2.5 times 10 to the minus 2 is this value. We know to get rid of this natural log, we have to exponentiate both sides. When we exponentiate, we're going to get K2 over 2.5 times 10 to the minus 2 is going to equal a value of 4.15. And when we cross multiply, we're going to find that K2 is equal to 0.104. The units are the same as K1 per second, which is going to go up. It goes up a fair bit because our temperature has gone up a fair bit, and this relationship is exponential.